Time to revisit induction. We of course saw induction in extension 1, but in extension 2 we have more interesting induction problems. Now the thing to remember with this is you're going to be held to a higher standard than extension 1 because you're doing a whole topic on proof. But let's just recap the ones we did see in extension 1. The first type we saw were these series type of questions. So an example of that I've written in some notation. We want to prove this particular expression. The first thing we would do is prove it true for the first case. The first case in this one is n equals 1, and that's another difference I guess with extension 2 and extension 1. In extension 1 the first case usually is just that, n equals 1. Now it doesn't have to be, but you usually see that in extension 1. Extension 2 could be anywhere. Right, left hand side, sub in r equals 1 into that sum, and we get 2/3. Now remember to show the substitution step. Don't just write the answer down, because you're showing it's going to be true for n equals 1. You need to show where you get it from. Right hand side, substituting into that, we also get 2/3. So yep, the left hand side does equal the right hand side, so hence it is true for n equals 1. Then we go and assume what it is that we're trying to prove. Remember, write the assumption down. Oh, and by the way, I should have said, when you start your induction proof, the first thing you should do is write down what you're trying to prove. Just because it's on the question paper doesn't mean you don't write it down. I mean, it is a proof. Someone is reading your solution. They want to know what it is you're trying to prove. So the first thing is write what it is that you're trying to prove. Now let's go back to here. My assumption then, r will now equal 1 to k instead of 1 to n. Inside the sum, that doesn't change, that's still what we're substituting into. And on the right hand side, again, I'll just replace n with k. We want to prove it true for the next case. So again, write down what you're trying to prove. This time the sum is going to k plus 1. And on the right hand side now, it'll become, well, that fraction will become 2 over k plus 2, k plus 3. Okay, here's my proof. The series type of question we can always rewrite by pulling out the last term from the series, because then we're left with our assumption, because the assumption was sum of all the other ones. So I've done that, I've pulled out the final term then, the term when it was k plus 1, substitute in the assumption. Now if it's not immediately obvious what you've done, then you would possibly write down, oh, by assumption. I've done this by assumption. Now this one I thought was kind of obvious. I didn't write it down. Mind you, it doesn't hurt to write it down anyway. We now want to play around with this algebraic fraction. Now I look at what I'm trying to prove. I already have the 1, so I'm not going to play around with the 1. I'm not going to put that into the fraction when I'm going to have to end up extracting it out again. So it makes no sense. But I will pull the other two pieces together into one algebraic fraction. The common denominator, k plus 1, k plus 2, k plus 3. Remember there's a negative out the front, so that 4 becomes negative 4. Playing around with the top of the fraction and factorising, bit of cancelling, and I'm pretty sure that is what we had to prove. Now remember, this part of the induction proof is actually a deductive proof. So you conclude it with your if-then statement. Now how you write it can be different. I've actually written it backwards and gone, hence the result is true if it's true for n equals k, but the if-then statement you could say, well, if it's true for k, then it's true for k plus 1. It's an if-then statement. And then we tie it all together. So the final thing you do is actually induce the solution. You're putting together what you just proved, this deductive proof, along with what you proved for n equals 1. You're pulling the two things together. And so when we tie it, we say, well look, we know it's true for n equals 1. And because I've just proven it true for k plus 1, then it's got to be true for every value by the induction process. That's all we really need to write. I know it's true for 1 because this just logically flows from what we've just said. I've said hence it's true for this. Well, since I know it's true for 1, then I must be able to induce every possible solution. But just like you did with the contrapositive, you said by contraposition, or you say by contradiction, you would say, oh, well, I'm doing it by induction. So which method of proof am I using? Here's an older one. It is a series type, but instead of going plus, 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 it went times, times, times. You'll notice it came from an extension 1 paper, actually. Okay. And this time we're starting with n greater than or equal to 3. So my first case will actually be n equals 3, which is the first term here if you have a look, because if I was to substitute into this general term I would get 1 minus 2 over 3, which is a third. And the right hand side, yes, we get a third as well, so yeah, left hand side does equal the right hand side, hence it's true for 3. My assumption, well this time I'm not only going to assume it's an integer, I need to specify it, but this integer is going to be greater than or equal to 3. That may or may not be useful in my eventual proof. I might end up using the fact that this number is bigger than or equal to 3. So I put it in my assumption. These are all the things I'm assuming. Okay. We want to prove it true for the next case, and we'll proof, well, just like the series ones where we go plus, 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 this is no different. We're just going times, times, times. So you notice I've extracted out the last one and we have the assumption there. Let's substitute in the assumption. So we're now saying it's 2 on k minus 1 times that last term. Well, in this case, it makes sense to turn that second one all into one fraction so we can play around with the algebra, and hopefully we can end up showing this is 2 on k plus 1. Well, k plus 1 minus 2, that is k minus 1, and we can say, yep, look, the k minus 1 cancels. We've got the 2 on the k plus 1 that we wanted. So hence it is true for k plus 1, if it's true for k. Remember my conclusion here, don't just fall in the habit of just, writing the standard, since it's true for n equals 1. Well, no, in this case, since it's true for n equals 3, then it will be true for all integers bigger than or equal to 3. The other type of problem we looked at in extension 1 was the divisibility type. So I'm going to prove n squared plus 2n is a multiple of 8. If n is even, so n has to be an even number for this one. Well, the first even number is n equals 2. That'll be my first case. 2 squared plus 2 times 2 is 8. Well, yes, 8 is divisible by 8. Now, it is a multiple of 8. So I know it's true for n equals 2. I would assume it's true for n equals k, but specifying k is an even number. So k squared plus 2k is equal to 8 times some integer. My assumption is, yes, p is an integer and k is an even number. They're the two assumptions I'm making here. We want to prove it true for the next case, but because we're talking about even numbers, the next case would be k plus 2, not k plus 1. So k plus 2 squared, and so on, also is equal to 8 times an integer. It would be a different integer. I've called it q. Proof. Okay. So the left hand side here, somehow I have to get my assumption in. My assumption was k squared plus 2k. So I play around with this, and what we have is k squared plus 4k plus 4 plus 2k plus 4 when I expand out. And I can see, well look, I've got a k squared and I do have a 2k as well. So there's my 8p, but then I also have 4k plus 8. Okay. When I factorise the 8, remember we're trying to show it's 8 times something. Woo, I got k on 2. But that's all right because we assumed k was an even number. So it is fair to say that k on 2 will be an integer because we assumed k was even. A p we assumed was also an integer. So yeah, that whole thing is an integer, and I write that down. Well, yeah, q is equal to that, but I just remind them, well, as k is even, I can say that is an integer. So I explain myself. Well, how can I make this conclusion? And then we just go into our pattern. But this time, hence it's true for k plus 2. If it's true for k, and then we can say, well, since it's true for 2, then it'll be true for all even numbers by induction. Of course, I could have done that proof a different way. If I had assumed n was equal to 2k, and then k could just be an integer, that also forces it to be an even number. So that's another way I could have done it. So my assumption would have then been 4k squared plus 4k is 8p. I'll prove it true for 2k plus 2. That would be the next even number. So this is what I want to prove. And in this case, again, I want to get my assumption in. So I want to find 4k squared plus 4, and it's there when I expand it out. But this time when I factorise the 8, I just get p plus k. But that's okay, because in this case, I assume k was an integer. whichever way you want to go, really, isn't it? You can assume k is even, or just make n equal to 2k. That forces it to be even as well. Hence it's true, etc., etc. That brings us on to inequality types of induction. So we're going to prove 2 to the power of n is greater than n squared. You see, we don't tend to see these in extension 1, but of course in our proof topic we've dealt with inequalities. So we do see these ones in extension 2. Well, the first integer greater than 4 is 5. So I want to prove the result is true for n equals 5. Well, the left-hand side is 32, the right-hand side is 25. Yeah, 32 is certainly bigger than 25. So it does work. We'll assume, but in my assumption I mentioned, well, look, k is bigger than 4. So in other words, I'm going to assume that 2 to the power of k is greater than k squared, but I'm also, going to assume that k is bigger than 4. And for this proof, that actually is going to be crucial in our proof, that part of the assumption. We're going to prove it's true for k plus 1. So I want to show, I'm using the technique, let's pull everything to the left-hand side. I'm going to show 2 to the power of k plus 1 minus k plus 1 squared is a positive number, is greater than 0. Okay, here's my proof. I've got 2 to the power of k plus 1 minus k plus 1 squared. Remember, we want to get our assumption in there. We have 2 pieces of the assumption we can use, but 2 to the power of k is greater than k squared is what I'm looking for. Well, the 2 to the power of k plus 1, I could rewrite as 2 times 2 to the power of k. So that will be greater than, because the 2 to the power of k is greater than 2k squared. So that'll be greater than 2k squared minus k squared minus 2k minus 1, which is, notice the signs, because you're saying, how do I get from one line to the other? I don't put a greater than sign here, because I'm saying, well, look, this second line is actually equal to the third line. And what we do is we read down. As long as we go down, the inequality signs are preserved, we're okay. We can replace it with an equals, that's fine. Anytime we've got an equals, I just can't replace it with a less than, because then I'd have one line that's saying greater than, one line that's saying less than, and that wouldn't make sense. All right, let's look at this k squared minus 2k minus 1. Well, hang on a sec. Remember, we said k was greater than 4. Well, if k is greater than 4, then k squared must be greater than 4 squared. And k is greater than 4, so we actually get that that is greater than 7. And that, of course, is bigger than 0. So hence it is true for k plus 1, even if it's true for k. And then, but when we write our conclusion, the first case is n equals 5, then it's true for all integers, and so on. Let's do another one. 1 plus 1 on 2 squared and so on is always going to be less than or equal to 2 minus 1 on n. Prove the result's true for n equals 1. Left-hand side, the first term is 1. Right-hand side is also equal to 1. So yes, it is true to say that's less than or equal to. Remember, it's less than or equal to. Well, I just showed it was equal to, so it is true to say it's less than or equal to. It's equal to. Okay, assume true for n equals k. There's my assumption. Prove for the next case. This is what I want to prove. Once again, I'm going to pull everything to the left-hand side and try to show this is always less than or equal to 0. So a negative number or 0. Here's my proof. Well, it is much like a series type. So let's pull out the term before, and then I can substitute in my assumption. We said all of that was less than or equal to 2 minus 1 on k. So this is what I've now got. 2 minus 1 on k plus 1 on k plus 1 squared minus 2, well the 2 minus 2 will disappear. And I'm left with this algebraic fraction. Well, let's make it all one fraction. The common denominator will be k plus 1 squared, and that's what I'm left with on the top. That's negative 1 when we play around with the top. Well, that's less than 0. Right? That is less than 0. How do I know that? Well, k, remember, was a positive number. K plus 1 squared is certainly positive. So the bottom of the fraction is a positive number. The top of the fraction is negative 1. Well, a negative divided by a positive will always be negative. So yes, that is less than 0. And I'll explain why I can make that conclusion. Well, because I know k is a positive number. I know that. That's why I can make this conclusion. So hence it's true for k plus 1, if it's also true for k. All right. The idea of induction then. Now this one's a little bit different. These ones are ones where you might use a diagram or a picture to explain yourself. It's not one that is nice, neat algebra. So they've given us this picture. We've got these walls and they meet in a corner there. A cube is placed in the corner and then we form a shape by placing more cubes onto this shape. And you can either stack it vertically or horizontally. Now this one is where they've ended up using 9 cubes. So n is going to be the number of cubes to make the solid. We're going to use induction to show that the number of exposed faces, the number we can actually see, so it's not up against the wall, it's not on the floor, is 2n plus 1. We'll prove the result is true for n equals 1. Okay, well that's what it would look like if n is equal to 1. There'd be 1 cube there. And I can see we have 3 exposed faces. Well, when n equals 1, 2n plus 1 is 3. So it is true. When there's 1 cube, we ended up with 2n plus 1 faces exposed. So it does work for n equals 1. I'm going to assume it's true for n equals k. So in other words, we're going to assume that when we have k cubes there'll be 2k plus 1 exposed faces. We want to prove for n equals k plus 1. So we want to prove that when there's k plus 1 cubes there, we'll have 2k plus 3 exposed faces. This is how I ended up explaining it. I drew a picture. And I said, well look, what I'm doing is, here's my little picture and I'm saying there's k cubes. And I'm going to add another cube to this picture. That's where I'm going to put it. I'm going to put it there. Now the addition of that new cube will end up covering one of the existing faces. Doesn't matter where I put the cube. When I add it, it will cover up one of the exposed faces. That will always happen. And we will end up with something like that if I placed it in that position. So that shaded one has now been covered. So I have 1 less. But by adding the cube, I then have 3 more exposed faces. So I've lost 1, but I've added 3. So the number of exposed faces for k plus 1 cube will be the number of exposed faces of k cubes minus the 1 I lost plus the 3 new ones. So it's 2k plus 1 minus 1 plus 3, 2k plus 3. And that was what we wanted to prove. So using pictures to do my explanation. Hence it's true, etc, etc, etc. The next type of induction question involves these recursive formulas. You might recall recursive formulas from when we looked at series and sequences. It was another way of writing a pattern. It's when we define the term, the general term, in terms of previous terms. Recursive formula is defined in m preceding terms. So then you would need to prove it true for the first m terms. So it might be more than just proving it true for the first case. You might have to prove it true for the first 2 cases. Things like that. And then you'll assume it true for n equals k. Well, I've gone backwards, so k minus 1 and so on. But again, you will need as many assumptions as there are terms in your recursive formula. The mistake a lot of people make is to try and prove the recursive formula. That's not what you're being asked to prove. That's being given to you as a fact. So you don't need to prove that, you can use it. Let's start off with this one. Here's our sequence. They've given us the first term, it's the square root of 2. Every term after that will be the square root of 2 plus the previous term. So in this case, there's only 1 term in the formula that we'll be substituting in. We're going to prove that every single term will be less than 2. Every single one will be less than 2. Prove it true for the first case. It's still the same idea. Prove it true for the first case. Well, they told me the first one was the square root of 2, and the square root of 2, it's around about 1.4. That's less than 2. So yeah, it is true for the first case. We will assume it true for n equals k. So I'm going to assume that the kth term is less than 2. Now in this case, I only need 1 assumption because I'll only be substituting 1 term into the recursive formula. We're now going to try and prove that term k plus 1 is less than 2 as well. And so that's where we can use our recursive formula. So we'll start with that. And that is how I'll get all these assumptions in. So I've assumed for each of the terms that I'm going to substitute in. In this case, there was just 1. So I've assumed that term k is less than 2. So this expression must be less than the square root of 2 plus 2. Well, 2 plus 2 is 4, the square root of 4 is 2. So reading down, yeah, ak plus 1 is less than 2. We've got our proof. So hence it's true for k plus 1 if it's true for k, and so on. Okay, so the actual method's exactly the same. Here's one, a classic recursive formula, the Fibonacci sequence, where each term is defined by adding the two previous terms together. So we actually need two terms in this formula. So that means we're going to have to prove it true for the first two numbers, because I'm going to have to substitute in, and they've actually given me the first two. They've told me that the first two are both equal to 1. That is your classic Fibonacci sequence. It goes 1, 1, 2, and so on. It's all right. N equals 1, let's go and prove that. Well, on the left-hand side, term 1, they told me is 1. On the right-hand side, let's sub it in. 1 plus root 5 on 2, the golden ratio, to the power of 1, which is, well, to 2 decimal places is 1.62, but yes, the left-hand side is less than or equal to the right-hand side. That is true. Now let's do it for n equals 2, and they told me term 2 is also equal to 1. On the right hand side it will now be squared, and that becomes 2.62 and something. Well, yes, the left hand side is less than the right hand side, so it is true for both 1 and 2. Now we'll make our assumption, but we need two assumptions. I've gone k and k plus 1 this time. I could have gone k and k minus 1. It doesn't really matter. I just need two consecutive terms here. So k and k plus 1. So I'm going to assume term k is less than 1 plus root 5 on 2 to the power of k. And I'm also going to assume term k plus 1 is less than 1 plus the square root of 5 on 2 to the power of k plus 1. We are now going to prove for the next term, which is k plus 2. Again, I'm going to use the idea of pulling everything to the left, and in this case we'll show it's negative. Well, the recursive formula, remember, was ak plus 2 is ak plus 1. That's why we made two assumptions, so I can now substitute into those two terms. So let's do that. All right, I have to show that this expression is negative, and it has a common factor there of 1 plus root 5 on 2. Now remember, when we factorise, we pull out the lowest power. The lowest power in this would be k. So I'm left with 1 plus root 5 on 2 minus 1 plus root 5 on 2 squared. We've just got to play with those second brackets there. Now I know 1 plus root 5 on 2 to the power of k is greater than 0. That's not going to be an issue. So essentially what I want to show is the second bracket here is negative, because then the whole thing will be negative. Let's look at that piece. So let's play with it. Common denominator would be 4. My numerator would become that. Expand it all out, and yeah, that actually turns out to be 0. Well, therefore, I now know that my expression that I started with there is less than 0, and that's what I wanted to prove. So hence it's true for k plus 2, but if it's true for k and k plus 1, well, since it's true for 1 and 2, then it's true for all integers by induction. Let's have a look at this one from 2 years ago. It was a recursive one. Also involved the square root of 2, coincidentally. But here's the definition. The first term is square root of 2. The second term is the square root of 2 plus root 2. Third term, square root of 2 plus root 2 plus root 2, and so on and so on. So the actual recursive formula for this is the n plus 1 term squared will be 2 plus the nth term. We're going to use induction to prove this amazing result, that term n actually is 2 times the cosine of pi on 2 to the power of n plus 1. Wow, going to get triggered into all this. Okay, we're going to prove then. I can start off. What am I trying to prove? This is what I'm trying to prove. Okay? Prove it true for the first case. Prove it true for n equals 1. Well, term 1 then is 2 times the cosine of pi on 2 squared. Cosine of pi on 4 is 1 on root 2. We end up with the square root of 2. And that is what we were told that A1 was. So yes, it does work for n equals 1. assume the result is true. So I'm going to assume that the kth term is 2 times the cosine of pi on the power of 2 to the power of k plus 1. Prove the result is true. So let's do our proof. So reminder again, we're trying to prove term k plus 1 is 2 times the cosine of pi on 2k plus 2. I will use the recursive formula that they gave me, and then I can substitute in our assumption that AK is 2 cosine of pi on 2k plus 1. And just to remind everyone, I did that by assumption. I've subbed my assumption in. Now I'm going to use double angle results. See, 2 plus 2 cos, I'm going to rewrite as 4 times a half of 1 plus cos pi 2k over 1. Why that? Because remember our cos squared and sine squared results? So I can now say that that is a half, and just to highlight the double angle part of it, it's going to be a half of 1 plus cos 2 theta, and theta in this case is pi on 2k plus 2. Therefore I can say, well, that's cos squared of pi on 2k plus 2. Well, if that's a squared is 4 cos squared, then the a is 2 cos. And that was what we were trying to prove. So hence it's true for k plus 1 if it's also true for k. And since it's true for 1, and so on and so on. Alright, so that was an example of one that they did a couple of years ago. So 2E, a whole host of induction questions for us to look at.